Okay. So good afternoon and welcome to this BioBarr final event organized under the form of workshop. This is the agenda of today. So we have 3 hours of presentations. I will be the moderator of the whole event, and general information. So a duration of 3 hours, the language is English. The event will be recorded as anticipated by my colleague. 9 speakers representing the project beneficiaries and the project officer from the Commission. The objective of this event is to share the knowledge generated along 54 months of activity on PHA-based materials. I remind you briefly the rules for participants, so kindly keep your microphone muted along the entire workshop session. Disable the webcam for more bandwidth and better connection performance. Please use the chat on the right for commenting and or asking questions along the workshop. When your comment is directed towards a specific speaker, please tag it using, for example, the name format in the chat window to distinguish between a general comment. Speakers will do their best for answering live where possible, I mean probably after the own presentation. As alternative, please share with us your questions by email, and we will manage them soon after the event. Where possible, we will try to allow a brief time for question and answer at the very end of this afternoon. In this case, please unmute yourself to begin speaking when needed and consider using your camera during the discussion with the speakers. So, this was just a very brief welcome. Now I want to present to you the project coordinator of BioBarr project, who is Raffaello Prugger from Tecnoalimenti. So Raffaello, the floor is yours.
Okay, thank you, Mariana. Let me say hello to all participants, to the representative of the BBI, Anna Ruiz, and to all representatives of the project partners. I will now share the screen. I have a brief overview of the project, just to introduce you into the issue. Can you see it?
Yes.
Okay, so wait, I have to do presentation mode. But it's not. Okay, now I think it should be presentation mode. Okay, so my name is Raffaello Prugger, coordinator and director of Tecnoalimenti and coordinator of this research project. Now, as non-profit research and technology organization for the food industry, the mission of Tecnoalimenti is to scout and to search for new solutions across the domains and the sectors, and identify new trends and new needs of the food industry, and to elaborate all this information and to convert them into research and innovation initiatives for the food industry. And exactly like this started this project. Let me go back a little bit to the origin of this project. Now, we had already, before the beginning of the project, several years that we got and perceived a mounting interest of the food industry towards sustainable and sustainability concerns, especially regarding the packaging, and this probably for sure pushed by the consumer trend and by the markets. So incidentally, in this years, I assisted to a business presentation of Mr. Astori, who was the CEO of BioOn, that was illustrating their technology of providing bio-based and biodegradable biopolymers from feedstock through a fermentation. So I was really fascinated by this. And after the speech, I just went there and contacted him and asked him, Why are we not doing something like this for the food packaging? Because actually he was presenting it only for the as bulk material for the automotive industry. But for doing this, we have to have sustainable materials, and in this case we had it, with comparable properties to existing materials, barriers, sealing, retrofitting, availability at industry scale, and feasible cost. These are basically the needs of the food industry. After some days, he reflected about this proposal and he contacted me and said, okay, let's start, let's do. And this is the origin of the project. So we as Tecnoalimenti then looked around for recruiting and searching excellence partner to carry ahead this idea, and we found them. We found them in this consortium. We elaborated, there was also incidentally exactly a topic at the BBI level, so we could just convert all these initiatives, all these events into an industrial research project. So this is how it started. We recruited 3 RTOs that they will speak today: CNTA, Tampere University, and the Technical University of Denmark. We recruited 3 SMEs, Ichivendue, Tecnoalimenti, and beyond, and 1 large company, Kao Chemigraph. This is the group that carried ahead the idea. Duration 48 months plus 6 months of delay due to pandemics. We had some difficulties in reorganizing ourselves during that period. 3.78 millions of investment, of which 3.2 by BBI, European Commission, and the type of action is a research and innovation activity. General idea of the project, just general overview, but you will have much better insights, of course, by the speakers. So based on the BioBarr approach, the project started with fermentating molasses, which is a feedstock, which due to proximity reasons was used by BioBarr, with a proprietary strain of bacteria in order to produce in the vacuoles of the bacteria the compound PIJ, polyhydroxycanoates. They were separated from the other matter, purified, compounded, and processed into grains of PHA. This was done by this was basically optimization of the process towards a film making and not bulk for automotive, which was carried out by BioBarr. And after having finishing this process, unfortunately, BioBarr entered into financial crisis and had to quit the project. So this event, after first disorientation of the project partners, but became a new opportunity. A new opportunity for the project because all the project partners rearranged their activity, and we are able at this point to open up for testing more materials, more PHA materials for different producers besides BioBarr. So this was taken as a great opportunity of the project. Of course, it increased very much the effort of all the consortium because we had parallel lines going on, but allowed to gain much more insight and produce more robust technical knowledge and data regarding this experience and this research. So the project after that continued with several lines of PHA origins, film making process, which is not an easy task because of you will see later, because the biopolymer easily breaks when filming. Functionalization, which means on film, the project had to produce a barrier property because PHA has no barrier property or very low barrier property towards gas, oxygen, and water vapor. So the project had a process of lamination with other polymers or coating with metal oxides. This was then carried out as well on some producers. Then the topic was that packaging is not completed if there is no printing and no ink. So we had an important partner that produced natural compostable pigments, which do not interfere with the biodegradability of the materials, that were printed on top of the material. And then finally packaging in the food product, which is a croissant that was used as model product, with sealing and all the issues which are connected with the process of packaging. This is the overview of the project. You will hear today a lot of issues about all the details of each step. But just two more reflections. What are the results that we gained? We achieved, first of all, 3 PHA granulates of different producers. This was the challenge that we took. One was upscaled. A prototype of PHA reel at industrial scale was produced. A prototype of 3 functionalized PHA reels that improved the barrier, as I said before, of these gases, oxygen and water vapor. And 2 prototypes of novel green compostable inks, and finished product prototypes, packed croissants. This was the results that were coming out of the project. What are the lessons learned? I can hear somebody has the microphone not muted. Kindly, if you can mute, would be nice. Okay, the lessons that we learned during these 4 years of project are the followings. There is a high demand from the food industry worldwide. We are receiving continuously inquiries about biodegradable and compostable biopolymers from all around. So I think for application in the food industry and also in other applications, of course. So I think something is really moving on this level. There are still some technical difficulties because we are retrofitting the new materials into the existing equipment. And this, of course, means that the new material has to fit exactly to the properties of the previous materials, the commercial materials, the fossil materials. So this is not an easy issue. It needs still more fine-tuned research needs, different food stocks, formula, filmability, and improvements, and you will hear all about these issues in the speakers. And then also the important issue that we learned is also that there is a trade-off between properties. If you want something biodegradable, bio-based, compostable, you probably cannot get everything. You cannot get also the same properties of the fossil material. It's very hard. Usually there are some trade-offs that also the consumer should understand, the producer should understand, and so on, that probably are often also reflected then in the price. So this is what we learned from as experience from this important project. Okay, now just before passing the floor, I would like to thank all project partners for the valuable research. Despite the pandemic, which was not an easy issue to deal during research, something like this that happens is not an easy issue, but we were able to go on anyway. Let me thank also Anna Ruiz, the project officer, with a very supportive and helpful attitude that really helped all the project to go ahead in all his story and events, unfortunate and fortunate events that happened. And let me also thank the coordination team of Tecnamenti, first of all, Mariana Faraldi, who you all know, who is a really strong and determined lady, and this is a luck for the project. Maria Antonella Palermo as well, Marco De Vito, and Paola Bissolotti, who is dealing with reporting and administrative issues. Okay, this was my presentation, my introduction. I now pass back the floor to you, Marianna. Thank you.
Yeah, thank you. Thank you for this introduction, Raffaello. So now it is the time for the presentation of the project officer. So contribution of BioBarr project to BBIJU goals, final remarks. So Anna, the floor is yours. Anna, you are still unmuted. Okay.
I think now it's
Okay.
correct. No?
Okay, now it's fine.
Well, thank you very much. It's a big pleasure for me to be part of this final workshop of the project BioBarr. As you know, well, time flies because the project started in June 2017, and we have been working together 4 months. And it has been a big pleasure for me to work with you, and I hope to have been able to support you in all the project management activities. I know that this project has gone through different moments, but some of them may be more critical than others, but well, it was great. And I'm really thankful for the good work of the coordinator, because everything was very easy, communication, coordination, and everything has resulted in a very cooperation with BBI. And the same for the full consortium. Thank you so much, because I think you have achieved great advancements. Not yet there for commercialization, maybe many things, but still I think you did a very good job. So let me, today in this opening, or in these remarks, I wanted only to highlight, which has been very important for BBI, and the outcomes, and how all the work that you have done is impacting in the BBI goals. So in fact, this project has delivered important advances for the technology used to develop packaging solutions from bio-based materials, and more concretely to develop new bio-based and biodegradable food packaging materials by improving the barrier functionalities of the PHAs. And what it has also been great that you have reached even to validate these new materials in the food industry environment. And this is for sure a great contribution to the BBI goals. Here I would like to target or to mention one of the SIRA, the Strategic Innovation and Research Agenda of the industry, that is mentioned in the SIRA, the target to replace 30% of the oil bio-based chemicals and materials. For sure this project will contribute with the new bio-based solutions, packaging solutions, and also contributing to the reduction of the CO2 emissions. And for sure it has a great impact in the market, in the European market of the bio-based polymers, which will deliver new growth opportunities and competitiveness. And still, I think there is work to be done, but we are in the way to provide solutions that at least are same competitive, being cost competitive with their fossil-based counterparts. So,
Anna, sorry,
yes.
Anna, sorry for interrupting you. You are not showing the slide. Is correct or?
No, it's not correct. I wanted to show my slides, but well, I don't know what happened. You don't see now the.
No, we have followed your discussion, but we are not able to see the screen. I mean, if you want to try to launch once more. Maybe yes, you can go out and go on once more, just with the sharing the screen.
I thought that I was sharing, and now I don't know why. Maybe I don't know. The connection is not working well, but my computer is not able to share my screen. But still, well, I had some slides, but the message is clear. So the contribution of your project to BBI is very important, supporting the sustainable growth of the bio-based industry, and in particular for the packaging solutions. Still not there. I know this is a real project, and still there are many things to do. but what you have done in this project for sure will set the basis for future work. And last not least, BBI is really concerned about what's going to happen with this project, and in general with our projects after BBI funding. And in that sense, we will really would like to encourage to exploit what you have achieved, not to maintain or to keep all the results of this project in the room, but really to try to exploit what you did. Eventually, there will be new opportunities for funding in the new partnership, the continuation of BBI. Probably you have heard about that. That is the Circular Bio-Based Europe. And for sure, there will be opportunities for the bio-based plastics packaging food industry community. And now you have in a real level, why not? You can try for demos in the future, even to a pre-commercial scale via flagships. Only wanted to say, I remain at your disposal, even the project has sent. I'm here for the consortium. And last, please, thank you so much for all the work. The cooperation was great. And I wish you very good luck in the meeting of today, but also in the future for all the work that still will remain for the community. Thank you, Mariana.
Thank you so much, Anna, for your kind words, and thank you for accepting to participate to this event. Okay, so we can continue for maintaining the time. So next presentation is on PHA extrusion, and Ioanna Lati from Tampere University. Ioanna, the floor is yours.
Thank you, Marianna. Can you hear me well and see all the slides?
Yes, perfect.
Okay, hello to everybody. Good afternoon. I am Johanna Lahti from Tampere University in Finland. I am a senior research fellow in the research group of paper converting and packaging. And in this BioBarr project, our role has been to work with extrusion process of PHAs. And today I will briefly try to summarize to you what we have been doing in BioBarr relating to extrusion process and what we have observed and achieved during the project. This slide shows the table of contents, so I will briefly start with a very short introduction to biopolymers, bio-based polymers in general. Then I will have a few slides about PHAs and their properties in general. I will also share with you some information on PHA manufacturers, some examples which exist. And then I will focus on the PHA production and processing in BioBarr project. So first with the introduction. We all know that there are different types of polymers and especially biopolymers nowadays. And as seen in the picture on the right-hand side, we can categorize the polymers in different groups based on the raw material and also based on the degradability. So we can have bio-based polymers, which are based on renewable raw materials, compared to, for example, fossil-based polymers. And then we can have biodegradable polymers, which are, of course, different to these non-biodegradable polymers. And in this project, we have worked with these bio-based biodegradable PHAs. As we know, PLA, polylactic acid, is the most commonly used biopolymer nowadays. Of course, all these depends on the applications, but if we talk in general, it is a bio-based and compostable polymer that we can use to produce very nice packaging films, very clear films, but have also certain lack of barrier properties. PHA PHAs, polyhydroxyalkanoids, they are bio-based and biodegradable. There are different types of PHAs available. There is, for example, BHB, polyhydroxybutyrate, and then we can have, for example, polyhydroxybutyrate valerate, which is a copolymer form of BHB. And all these different forms of the polymer have different, for example, processability and also end-use properties. And the type of the polymer is also very important if we think about processing and the end-use properties. PBS is also a very common polymer or very much studied polymer, polybutylene succinate, and it is very useful polymer since it has polyethylene-like processing and also the properties. Then we can have, for example, starch-based blends and formulations which have certain limitations in barrier. In many cases, biopolymers need to be, for example, blended together to enhance the processability and also maybe the final properties. So this is something that you will hear also later on when we talk about processability. So PHAs in BioBarr and in general. So PHAs are linear polyesters which can be produced by bacterial fermentation. And as I already said, there are different forms of PHAs. The most common ones are polyhydroxybutyrate BHB and the valerate copolymer BHBV. And the form of the polymer affects on the properties. So for example, BHB is quite stiff, but it can be softened and by using the valerate form. They have quite high melting point and they resemble PP polypropylene in their properties. They are safe to use in packaging application and their disposal is suitable for these applications where biodegradability is targeted. And as you will see also in our project results, PHAs can be processed with normal processing equipment like extrusion. Of course, with PHAs, as with some of the other biopolymers, there can be some challenges which we also try to solve in this project. So PHA, for example, has quite narrow processing window if we talk about extrusion, and varying this valerate content we can affect on the processing in extrusion. Also, the crystallization behavior is something that causes sometimes challenges in extrusion casting processes or coating processes. So they typically crystallize very slowly, and this can cause, for example, sticking problems in the chill roll when producing through casting process. Also, this crystallizing can affect on the end-use properties of the film, for example, some shrinking effect. We can affect on this behavior by using nucleating agents, and this can be used beneficially to affect this process of crystallizing. Brittleness and the mechanical properties are sometimes challenged in post-processing and also in the end use. Also, there might be some challenges depending on what kind of grade we are using. That is the quality constant, if there are any variation in the quality of the material, if there is uneven quality in pellets, and so on. These all can affect on the processability and can be seen as for example, defects in the films. And this linear nature of the polymer, of course, may cause some typical features. For example, sometimes this high necking behavior in casting. In the following slides, we have collected some of the manufacturers and grades of PHAs. Some are in development stage, some are already commercially available. They are designed for different purposes. Some are mainly for casting, some are mainly for injection molding. Then these PHAs can also be blended or otherwise modified. And there are companies also who are specialized for this. And as mentioned already in the beginning, blending is quite typical way to affect on the processability of PHAs. I want to mention also that this list is not considered complete, so there might be some information missing or some manufacturers. These are just some examples. So 2 slides of manufacturers. We have Danimer first there, providing formulated PHA. Then we have BioBarr, which is producing PHB. We have Natureplast from France, Kaneka producing PHBH. Then we have Helian, which has a range of PHA Radox, and they are also a distributor of Tianan Biologic. I will not go through all these details. Then we have Aircross from Spain, also providing PHA-based materials. Grupo Maip in Italy, they have an I Am Nature series of PHB blend. Then we have Navigate, Implus from Spain, and lastly here on the list, Tianin Green Bio. They have also this So Green series of PHA products. So these are just examples of providers of different types of PHAs. Then we move to the actual topic of how we processed PHAs in this project and which grades we used. So this slide shows the BioBarr process. So our target was to extrude films for flexible packaging using PHAs from renewable raw materials. We did the processing with existing machinery, so the same extrusion machinery as we are processing traditional polymers. We had to tackle the typical narrow processing window of PHA in extrusion, and also the crystallization behavior, as I mentioned before, set some challenges. So we are using PHAs from renewable sources. They were in the first phase turned into granulates or pellets that we processed at Tampere University in extrusion. We casted them into films, and those films were then treated or laminated at Itzimenduhe, and then packed and formed and packed at Corsini to create bio-based packaging of bakery products. So this is how the process went. As mentioned already in the introduction, we had some challenges during the project. So we started with Bion material. So in the first phase, we used this Minerv material from Bion, and this material is obtained from sugar co-products, and it is a type of PHBV. And then due to some unfortunate issues, we didn't have Bion then anymore in the consortia, and we had to do some other options for material usage. And in the second phase, we tested 3 different commercially available PHA grades in the project. There is here some information on the Minerv grade from Bion. So they do first the production of the PHA powder, and then they formulated the powder into pellets or granulates that we then processed at Tampere University. So the process in the beginning was already a little bit explained in the introduction presentation, but everything starts from fermentation. Then we have the recovery phase, purification, and then we have the PHA powder, which was then modified into pellets that we used in our extrusion process. And what was important in this PHA production was, of course, the optimization of the recipe. So, for example, as I mentioned in the beginning, the composition of the polymer is very important for processability and the end-use properties. So, for example, the molecular structure and additives we use had to be taken into account when knowing what kind of filming technology we have and what kind of properties are targeted in the final film. We processed the PHA in different processes in BioBarr process. We tested the formulations in blown film process as shown in the pictures, and then in cast film extrusion process at Tampere University. This slide shows the facility that we have at Tampere University. So we have a co-extrusion coating and casting line with option for lamination also. And here we did the processing testing of different PHAs and also manufactured the films for later steps. Different grades that we tested. So I already mentioned the PHPV from Bayonne that we had in the beginning of the project, and we did several tests and trials with that material very successfully. And after that, we worked with 3 commercially available grades of BHP and BHPV. And the different materials were tested in blown and casting processes. So we produced films with these 2 processes in different thicknesses, less than 80 microns. We also tested PHAs in co-extrusion process, so in combination with other polymers like PLA and Ecovio from BASF. Corona surface treatment was also tested for the films for increasing the surface energy. And of course, we analyzed all the different important properties like barrier properties, water vapor transmission rate, oxygen transmission rate, grease barrier, sealability, and so on. And the results of this analysis work is provided by Chiara in the next presentation after me. So I will focus only on processing of the materials. So I said in the beginning that there are challenges and there are still challenges for the future. So I think that there are still room for new projects, like BBI representative also mentioned. So processing of PHAs has been done with existing machinery. So we were able to use the same extrusion machinery as with traditional polymers. As mentioned, PHAs typically have very narrow processing window, but we were able to find suitable processing window and this way produce uniform pinhole-free films for the further steps. This crystallization behavior set some challenges, but through our work, we were able to find optimal casting setup to avoid, for example, these sticking problems that may occur when using casting on a chill roll. Some challenges just to mention maybe for the future or for the future work, or when, for example, working with PHAs, important thing is, of course, the grade selection, meaning what kind of polymer you are using, what is your application, what is your process. So there are different grades available, as you saw. Some are suitable for injection molding, some are suitable for casting and so on. So not all are suitable for all processes, I would say. So you really need to to know what kind of grade you are using. This crystallization behavior is still a challenge, and there are still things to be solved regarding mechanical properties and fragility of the film in post-processing. And in our view, since this project focused mainly on pure PHA, so meaning that we try to make the film out of pure PHAs, of course, this set some challenges, and of course, maybe in future we would be studying, for example, blending of PHA with other polymers, and maybe more on this co-extrusion technology or lamination. So this is something we partly already did in BioBarr, but not for example, this blending. So I'm getting to the end of my presentation, and I'm summarizing a little bit what we achieved. So in this project, we demonstrated different PHA grades for blown film and cast film production processes, and we were able to produce films for flexible packaging. Just to mention that in one other project, we have also demonstrated that now PHA is also for extrusion coating of fiber-based substrate. So just as an example of how PHAs can be used in different applications. And as mentioned on the slide also, PHAs can be processed with existing extrusion equipment, and depending on what is your process, what is your application, there are certainly different grades that you can find and use in your process to produce different kind of products, rigid objects, coatings, films, and so on. With this, I want to thank you for your attention, and if there are any questions, you can chat or you can email me or Marianna. Thank you very much.
Thank you, Joanna. I have seen that in the chat there are some questions, so in the meantime we go on if you want to read what is written there. So we can go on with Icimendue, Chiara Ascione, mechanical and barrier properties of PHA. Chiara?
Good morning. Can you hear me? I will share my screen.
Yes.
Okay. Can you see the screen and the presentation?
Yes, fine. Thank you.
Okay. I'm Chiara Ascione. I'm an R&D engineer in Icimendue, that is an Italian converter located in Marcianise, and I will discuss the mechanical and barrier properties of PHA. I will make a short introduction on the importance of the barrier and mechanical properties for a potential flexible packaging material. Then I will present the materials that we characterized and also the methods used for the characterization. And I will talk about the results obtained from this characterization. And then finally, I will make some final comments on the results obtained. Barrier and mechanical properties are very important for a potential flexible food packaging material. In fact, barrier properties, especially to water vapor and oxygen, establish the shelf life of the food packet, delaying its deterioration during the time. On the other hand, the mechanical properties of the flexible film used for the packaging are strictly related to its runnability through all the processes of converting and confectionery, and they are also related to the final visual aspect and handling of the packed food. At the moment, the use of bioplastic in this sector is still limited due to their poor barrier and mechanical properties that need to be improved. Usually for conventional plastic, there are several techniques to improve barrier properties of a polymer. The main techniques are, for example, the use of surface treatments that consist in the application of a thin barrier layer by physical vapor deposition techniques, like, for example, the metallization, the Elox treatment, or Cox treatment. The conventional aluminum metallization is widely used in flexible packaging, for example, for polypropylene, that is widely used as a metallized film to improve the range of the food that can be packed with an improved barrier of this material. Another route to improve the barrier properties of a polymer is the co-extrusion with the barrier polymer. In the step of extrusion of the film, a co-extrusion can be achieved with a barrier layer, like for example, that can be applied as core or external layer to the film, like for example happens for polyethylene that is co-extruded with EVOH in order to improve its barrier properties to oxygen. The co-extrusion could also increase the mechanical properties of a plastic film, but also give to him some further properties, like for example sealability, or for example tailoring its coefficient of friction. We focused our attention on the characterization of a commercial PHB grade provided by BioBarr. So we characterized this polymer for mechanical and barrier properties, and then we characterized two systems developed during the project: the surface-treated PHB films, in particular metallized PHB and Elox-treated PHB, and then we characterized the co-extruded PHB films. The co-extrusion was performed with two compostable polymers in order to achieve the complete compostability of to don't affect the compostability of PHB. The co-extrusion was performed with PLA and Ecovio, that is a polymer, a compostable polymer provided by BASF. The methods for the characterization of the mechanical properties, the method was the tensile testing according to the standard method D8082, that is the standard method for defining tensile properties of plastic materials. The tests were performed with a dynamometer to obtain a stress-strain curve. From the stress-strain curve, it's possible to calculate the tensile strength and the elongation at break of the film. For the characterization of barrier properties, we used the standard methods for the determination of water vapor transmission rate and the oxygen transmission rate. And the characterization were performed using a water vapor permeabilimeter and an oxygen permeabilimeter. Now I will present the results of the characterization. In particular, I will start from the surface-treated film, comparing to the PHB, the pristine PHB that is used as a reference to compare the data. As you can see, the value both of elongation at break and tensile strength of the PHB are very low, and also the same trend we have for the surface-treated films, as the thin barrier layer is not able to increase mechanical performances of the PHB. You can observe that from the shape of the stress strain curve that PHB is a fragile material, and this could be a problem in the runnability of this material through the main processes of converting and also of packing. These are instead the results obtained for the co-extruded film. Even if, as you can see, the presence of a co-extruded layer improved both the values of elongation at the break and tensile strength of PHB. But these values are still very far from conventional polymer used in flexible packaging, like for example, co-extruded polypropylene. The fact is that the presence of the co-extruded layer changed the behavior of the PHB from a fragile behavior to a plastic behavior. The fragile behavior of PHB also influences its behavior during the confectionery. In fact, the material is too fragile, and it can have a fragile breakage under the sealing juice. Instead, in the case of co-extruded films in which the behavior changes from fragile to plastic, it's possible to observe by the measurement of seal initiation temperature that the material can resist under the sealing juice, and also the range in which the material is sealable is bigger. Instead, for the characterization of barrier properties, the water vapor transmission rate was measured at tropical conditions, while oxygen transmission rate was measured at dry condition. It's possible to observe, as both PLA and EcoVio are not barrier polymers, compared to PHB, the co-extruded film results to have similar barrier properties to water vapor, and just a slightly reduction of the value of oxygen transmission rate that result to be still very high. Instead, in the case of surface-treated films, both the surface treatments are able to improve water vapor and oxygen barrier performances of PHB, as the decrease for water vapor transmission rate is more than 50%, and in the case of oxygen transmission rate, the decrease is more than 99%. And now I will make some final comments about the results obtained for the characterization of mechanical properties and barrier properties of the systems developed. The co-extrusion with another compostable polymer seems to be the most promising route for the improvement of the mechanical properties of PHB. Also, another possibility to improve the mechanical properties should be the blending of the material with other polymers, or to add some agents inside to make the material more plastic. In fact, as you can see also in this picture, in which are reported the samples of PHB and co-extruded PHB after the tensile testing, the co-extruded film present a plastic deformation to break, compared to PHB that instead has a fragile behavior to break. So the co-extrusion also, we verified that could increase the mechanical stability of PHA during the confectionery processes, increasing the range in which this material could be sealable. About barrier properties, was verified that PHB barrier properties result to be very similar to other bioplastics already used in flexible packaging, such as PLA. Instead, surface treatment, the presence of surface treatments, both metallization and Elox treatment, improve the oxygen barrier properties of PHB. So we can conclude that PHB results to be a potential packaging material for food that don't need a barrier, such as fresh food, for example, fruit, vegetables, and salad. Instead, surface-treated PHB films result to be potentially suitable also for bakery products or cheese, as they guarantee a high barrier to oxygen. I finished my presentation, and if you have any comments or question, you can write me also on my email.
Chiara, thank you for this presentation. I think you can go on with.
I will go on. Okay.
With the next one, which is strictly correlated with this one. So PHA functionalization techniques. So we go in deep into these functionalization techniques. Thank you.
Okay. Yes. Now I will discuss about PHA functionalization techniques. With the functionalization, we refer to processes using in converting to modify the properties of a film and also to confer to it a different visual aspect. We decided to focus our attention on three main processes used for functionalization in converting industries, that are the use of surface treatment to improve the barrier properties of the film, the lamination with another film, like for example PLA, and also the ink deposition. Then I will make some final consideration on the PHB feasibility through the processes analyzed. Also, as discussed also in the previous presentation, as a surface treatment, we refer to treatment in which by physical vapor deposition and thin barrier layer is applied on the surface of a film for improving barrier properties. This is a common method used in flexible packaging to improve the barrier properties of the films. And the main technique used is the conventional aluminum metallization. Also, it's used the Elox treatment, and it's starting to become more used also this COX treatment. With aluminum metallization, we define the deposition of an aluminum thin barrier layer deposited by vacuum metallizer, by a vacuum metallizer, and it is a very widely used techniques in flexible packaging, as it is a low-cost technique to improve barrier properties. However, this technique causes a metallic appearance of the films, so it compromised the transparency of the polymer. Elox treatment is also widely used in flexible packaging and consists in the deposition of a thin barrier layer of aluminum oxide, and is performed by the using of a vacuum metallizer, as happened for the conventional metallization, but introducing oxygen in order to oxidize the aluminum before the deposition on the substrate. This is a medium cost technique, as it requires the use of a protective layer, as the eloxytin barrier layer is quite fragile, but this kind of treatment doesn't compromise the appearance of the polymer surface, as the thin barrier layer is transparent. Another technique to obtain a transparent barrier layer is the COX treatment, that consists in the deposition of a thin layer of silicon oxides by a plasma coating equipment. That is a technique with a higher cost compared to conventional metallization and also Elox treatment. We started to perform, always considering the PHB, the commercial PHB, also discussed in the previous presentation. We have done some previous samples of PHB treated with COX treatment, but this treatment causes the formation of defects and pinholes on the surface of the film that compromised the barrier properties of PHB. So we decided to continue to investigate conventional metallization and just conventional metallization and Elox treatment. So we realized some prototypes on semi-industrial scale of metallized and Elox-treated PHB samples. We realized A4 samples putting untreated PHB on a carrier reel that was treated by an industrial metallizer in order to obtain metallized film and Elox-treated film. Both metallization and Elox treatment, as I discussed previously in the other presentation, are able to improve barrier performances of the PHB. And also, this treatment passed the adhesive tape test for the evaluation of the adhesion. Then we realized also a prototype on industrial scale of metallized PHB. So we realized the real PHB metallized reel that we used for packing croissant on the lab scale with a sewing machine to obtain a croissant packed with the functionalized PHB. Another technique that is widely used for the functionalization in converting is the lamination with another polymer. For PHB, obviously, the other polymer also needs to be compostable. So we decided to perform the lamination with the PLA. We realized prototypes of PHB PLA laminates using a compostable water-based adhesive by rod coating techniques. We tried to make different configuration of the laminates in order to reply what happened on an industrial lamination machine. In fact, we decided to make different prototypes, changing the choice of primary layer and secondary layer. As primary layer, we define the layer in which the adhesive is applied during the lamination. As you can see in the first two configurations, PHB is chosen as primary layer. From one side, matte side and gloss side. In the third configuration, PLA is chosen as a primary layer. As you can see, when PHB is used as primary layer, there are several defects, like for example, like bubbles or folds on the prototypes, due to the fact this doesn't happen in the case in which PLA is applied as is chosen as primary layer, due to the fact that PLA has higher weightability for the adhesive used compared to PHB. The configuration tree in which PLA is chosen as a primary layer seems to be the best results, both in terms of appearance of the prototypes realized, but also in terms of the strength of the final laminate. According to this configuration, we decided to perform the realization on the industrial scale of a prototype of a real PHB PLA laminate, in which PHB was chosen as a secondary layer and PLA was chosen as a primary layer. The lamination was performed using a bicomponent solventless adhesive in order that was deposited on the primary layer, that in this case was the PLA. We decided to use a solventless adhesive in order to don't stress further the PHB material with the temperature and with the use of a solvent. The PHB before the lamination was treated by corona treatment in order to improve its wearability. So we realized the PHB PLA laminated reel. The lamination is an important technique in flexible packaging because it is widely used in converting, for example, for internal printing application. The presence of PLA could also increase the runnability of PHB through packing processes, as it reduces the fragile behavior of PHB. PLA can also be metallized or alox treated to improve further the barrier properties of the laminate. And as you can see in this picture, PLA confers also to PHB a gloss appearance. As final functionalization, we investigated the ink deposition on PHB. The ink deposition is very important in flexible packaging, as is used to make a packaging recognizable on the market, but also to give to the customer some information about the food products. We decided to investigate the use of conventional inks used both in rotogravure printing and also in flexo printing with different chemical natures. For example, we investigated nitroacrylic and nitropolyurethanic inks that are usually used for printing polypropylene, and also a vinylic ink that is commonly used to print polyester. Then we also made some tests on the deposition of a compostable under development ink that is a water-based ink for flexo printing. Then after the deposition, we performed the adhesive tape test after 24 hours from the deposition of the ink. The conventional nitroacrylics and nitropolyurethanes inks, even without the using of an hardener, result to have a good adhesion on PHB surface. So we decided to make also a prototype on semi-industrial scale for the ink deposition on PHB. In particular, we made the test using a gravure-proof press machine that reply one element of the rotogravure machine. As you can see in the picture, there is a rotogravure cylinder in which the ink is applied on, and the rotogravure transfer the ink on the surface of the film. In this case, an under development water-based ink was deposited with the rotogravure cylinder, and also in this case, the addition of the ink on PHB results good, as it passes the test of the adhesive tape test after 24 hours. So we demonstrated that during the project, we demonstrated that we were able to realize prototypes on lab scale, but also on the industrial scale of main functionalization techniques used in converting, realizing a PHB metallized reel, inked PHB reel, and also laminated PHB PLA reel. PHB resulted to be compatible with all the other materials used in the realization of the prototypes, and it also, even if it is a fragile material, it successfully ran on the main processes regarding the functionalization and converting in flexible food packaging. So thank you for your attention again.
Thank you so much. I think there is a comment in the chat. So Chiara, if you want to read soon after. In the meantime, we proceed and go on. Next presentation is from Cow Chemigraph Benjamin Moreno, new compostable inks. Benjamin,
hello.
Hello, we can
Good
hear
afternoon,
you.
everybody.
We cannot see your presentation yet.
A moment, please. Sorry. Now. Okay. Well.
Okay.
Hello. My name is Benjamin Moreno, and I have been working at Cow Chemigraph for 26 years. My entire career in the company has been linked to water-based inks, and I am currently in charge of R&D for these products. Cow Chemigraph is a world reference company in the production of inks and varnishes for flexography, gravure, and digital printing systems. From 1970 until now, our company has always been leading the development of new products. With incorporation to the Cow Group, our research lines have been oriented toward sustainability, and an example of this is the BioBarr project. Cow's commitment to sustainability has led us to achieve the EcoVadis Platinum Award this year. Well, the table of contents of this presentation are: first, compost water-based ink optimization, after development of a new bio-based ink, and finally, printing process validation. As a first step in the project, we have worked on optimizing the Hydrostar OK Compost series inks. These inks have the EN 13431 certification, but are formulated with non-renewable raw materials. In the picture, you can see how the solvent, in this case water, the resin and the pigments are the three major components of the ink. The rest of the substance present are additives, deformers, waxes, preservatives, and all of them together don't represent a significant percentage of the ink. However, their function is essential for the ink to work properly in the printing machine and to have got resistance once printed. The optimization that we have carried out consisted of replacing those additives for which we found a renewable alternative. First, we contacted our regular suppliers and other new ones looking for products of renewable origin. Next, we verified its compatibility with the standard matrix, and finally, we evaluated its effectiveness and the interactions of other properties of the ink. For instance, with the deformers, we checked their dispersibility, because if the deformer is not easy to incorporate, it will be probably produce printing defects. We checked also their effectivity in a short, medium, and a long term. It means the volume of foam generated in the ink and the time needed to remove it. Finally, we check also their interactions with the slip and gloss of the ink. With another substance, waxes, wetting agents, dispersed, a similar process was carried out. At the end of all this work, we selected the formers based on general vegetal oil, waxes of the Carnauba palm, and some surfactants obtained from coconut, soya, or another plants. After making this change, the Hydrostar OK Compost ink series has been keeping the same features: pigment concentration, gloss, rub resistance, printability, and the conditions to print them remain the same. For the print viscosity, with rubber taping roller, the traditional inking system, between 19 and 24 seconds in 4-Cap4, or between 23 and 28 seconds in closed chamber with a scraper or doctor blade. The print speed varies depending on the airflow available in the printing machine and dryer temperature. As general information, the standard speed in flexo machines with water-based inks on plastic film is about 200 meters per minute. Currently, we are manufacturing our Hydrostar OK Compost series products with renewable or partial renewable raw materials discovered during the BioBarr project. Its technical data sheet shows this fact, as you can see in the slides. Our society is increasingly sensitive to the environment. The use of compostable packaging is one of the solutions that companies can give their products to satisfy consumers and enhance their corporate social responsibility. Brands as Amazon, Colgate, Alter Eco are replacing their traditional packaging, and compostable inks could be a good solution for the customization of the new ones. The second step in the project has been the development of a new bio-based inks. The goal in this part was to replace the resins and organic pigments that we have seen are the major components of the inks. As you can see in the slide, the manufacturing ink process is made up of two different lines that join at the end. One is the production of pigment concentrates, and the other, the production of technological varnish. The pigment concentrates obviously have the function of forming the final color, while technological varnish provides the main characteristics of the ink. Therefore, the varnish is different depending on the type of material to be printed and the requirements that we ask of the final printing: physical and chemical resistance and regulatory compliance. To carry out the development of technological varnish to print on PHA, besides the technical work, we have tried to open our minds and test materials not used to produce inks and contact with suppliers who are developing new products. We have tested soy or milk proteins, rice starch, rosin resins obtained from trees, PU and acrylics polymers obtained from vegetal polyols, aqueous emulsion of PLA, or vinyl acetate resin synthesized with acetic acid extracted from wood. The main challenge related to the new ink development have been and are a good stability, to have adhesion on PHA film, get a good water resistance, the resolution of ink, achieve a good film formation, to avoid taking or blocking, obviously a reasonable cost, and the incorporation of new products during all the project. In fact, we are currently still testing new materials. Finally, the best option from different prototypes designed has been chosen. This prototype varnish that we are named RMV technological varnish has a good balance from percentage of bio-based materials, 40% in weight, cost, printability, adhesion, and resistance. It could be printed on paper or plastic films. About the other line in the manufacturing process, the pigment concentrates, the challenge is and will be for a long time how to replace them. Currently in the market, among the standard pigments, only one manufacturer is producing the quinacridone pigment, PR 122, with a renewable part. The rest of the usual pigments used in printing ink are manufactured from non-renewable raw materials. Other organic pigments, green chlorophylls, red, orange, or yellow carotenoids that are obtained from vegetables or algae are too expensive to produce inks. These pigments are being used only in cosmetic products. With this scenario, the inorganic pigments seem the best option to reduce the petroleum derivatives, but unfortunately, only some of them comply with the European regulation on food packaging, and this involves a short range of colors. By mixing technological varnish and inorganic pigments concentrates, yellow, red, black, blue, and white, we have obtained a new series of inks, Hydrostar RMV, that represents a breakthrough in the market. With these inks, the reduction of raw materials obtained from petroleum is between feed for white already manufactured with inorganic pigments from time ago, up to 40% for inks with high color intensity. Regarding the print validation process, the final part of development, the results in laboratory tests are good and seem to be reproducible in the industrial printing. An industrial test is ongoing for verifying the stability in the printing machine and the quality of printings. Like the standard inks, printing conditions and final formulation of inks are related and will not the same for all the applications. Well, that is it. If you have any questions, you can contact me by email. Thank you for your attention. And Mariana, you can continue, please.
Yes, thank you so much, Benjamin. Okay, we are perfectly in line. We can continue with CNTA, Eva Petri, PHA in contact with food, migration tests. This is for sure an interesting aspect to take into consideration. Eva, the floor is yours.
Okay, thank you, Mariana. First of all, I would like to thank all people for your attendance today. So good afternoon. Let me introduce myself. I'm Eva Petri and I work at CNTA in the research and development area. So CNTA is the National Center for Food Technology and Safety, and it's located in an industrial area of vegetables preserve nearby Ebro Valley in Spain. Within the project, we have been responsible for the migration and biodegradability tests. So I'm going to present the migration testing results. This is the table of contents. We will go through a brief introduction. I will describe the testing methodology, and I will go through the migration results and some final comments. So, food contact materials, which as its name suggests, are materials that are intended to be in contact with food. So they must ensure compliance with European regulations, and they do not transfer any substances from the package to the food because it constitutes a risk to the consumer. Therefore, they are under under the legal umbrella of this regulation, which says that the release of substances from food contact materials should not bring unacceptable changes in the chemical composition, endanger human health, or bring a deterioration in the organoleptic properties. So the risk assessment covers these potential migrations, the overall, specific, and sensory migration. And if those three migrations are okay, the migration testing is also okay. So we are going through the testing methodology. Two types of testing have been performed within the project. We have the testing by total immersion, this one, in which both phases of the sample are in contact with the simulant, or the single site testing using a migration cell. In this case, only one surface of the material is in contact with the simulant. Afterwards, a 14 centimeters by 14 centimeters film sample is placed in the migration cell. Then it's closed and filled with a simulant. Afterwards, the migration cells are incubated in an oven, and for the overall migration, there is a stage of evaporation of the simulant and wait, and for the specific migration, there is an instrumental analysis. Sorry. Yes. According to the food simulants, it's often impractical to perform migration tests on actual food under real conditions. Therefore, the tests are performed on food contact simulants under simulated test conditions. So, determining which simulants apply will vary based on the food contact application intended use. In our case, we use simulant A, which is assigned for non-acidic foods. Also, food simulant B, assigned for acidic food, and food simulant D2, assigned for fatty foods. Regarding the selection of the test condition, we have to select the contact time and the temperature. It's also covered by the legislation, and there are some standardized conditions for testing. In our case, we selected this one, 10 days at 40 degrees. And we have also to fulfill with the legislation, so there are some limits for the overall migration. The limit is set in 10 milligrams per decimeter square. And in the case of a specific migration, where there are a maximum permitted amount of a given substance released from a material. And if there is no maximum permitted, there is a restriction, and the limit is set in 60 milligrams per kilogram. Regarding the testing methodology used in the sensory testing, we have these test conditions, which is also covered by these standards. So in this case, we put inside a glass jar a food simulant. In this case, is milk chocolate. So we put, as it's represented in the picture, the chocolate and the film sample to be tested. Afterwards, we incubate this jar for 2 days at 22 degrees, and we perform a discriminative sensory testing, specifically a triangle test, where 3 samples are given, and one of the samples is different from the rest. So panelists are asked to identify which is the odd sample. So these are some pictures of the appearance of film sets that were received at CNTA from different providers. And as shown in the table above, along BioBarr project lifespan, different PHA pellets were tested for a total of 19 trials. Some of them have been analyzed as pure PHA, some others already functionalized with lamination and or with surface treatment. Some trials were repeated on the same batch, and others involved different batches, different production stages. So regarding overall migrations, in this case, in the table in the upper side, we can see that all samples comply with the overall migration limits for simulant A, this one, and for simulant B, this one. But as can be seen, there is an optimization of the. There is no compliance for simulant D2. But as can be seen, there is an optimization of the pH grades along the subsequent production batches, where we can see that the values are decreasing. So migration results obtained after each one of the productions were incorporated into the decision-making process, which help in the improvement of the technical aspects related to their potential use as food packaging. And in this case, we have that PHB samples comply with the overall migration limit also for simulant A and for simulant B, but largely exceeded the overall migration limit for simulant D2. This may be due to the presence of oil and lubricant in the migration cell. But compared to functionalized samples, we observe that in this case, there is a high decrease in the overall migration values, indicating that the surface treatment acts as a barrier to compounds.
No, es que callada al final, me cago en la puta. ¿Sí? Pero bueno, da igual. O sea...
Regarding the specific migration, a list of substances has been generated to check the components authorized and the limit applicable. Here we've got which is the maximum permitted amount of the different compounds analyzed. And as we can see, all samples tested comply with the specific migration limit for compounds evaluated. According to the sensory integration, we have that from statistical tables in a triangle test, the number of correct responses for significance when 12 judges are involved is 8. So in this case, we have that all responses were less than the critical number, less than 8. So there is not enough evidence to conclude that there is a difference between both samples. So they can be considered to be suitable for being used in direct contact with food, and they do not bring any changes to the composition or organoleptic characteristics of food. In this case, it will be chocolate. So in general terms, all samples evaluated have complied with the overall migration limit for simulants A and B. However, simulant D2, which is assigned for fatty food, has presented values above the limit in some cases. So the selection of this simulant was done to mimic what might happen in the food model chosen within the project. That, as Joanna has said, it was a bakery product, a croissant. So these problems encountered during the migration test with simulant D2 show that the test procedures set in current legislation regarding plastic materials may not be suitable for all new-based materials. Also, samples evaluated have complied with the specific migration limit for all the substances. Data obtained via sensory assessment confirm the quality properties of PHBB and PHB film samples tested in comparison with the reference sample. And regarding PHB functionalized samples, they comply with the overall and specific migration limit in all cases studied. Compared to non-functionalized counterpart, it was observed a high decrease in the overall migration values, indicating that this surface treatment acts as a barrier to compounds migration. So that's all from my side. Thank you for your attention. And if you have any question, you can mail me or send a message. Thank you.
Thank you so much, Eva. Okay, we can continue with the same organization, CNTA. In this case, Jorge Lorenzo will present PHA compostability and biodegradability. So for sure, this is a topic of interest for understanding the environmental impact of these new materials. So Jorge, the floor is yours.
Okay, thank you, Mariana. Can you see my presentation?
Yes.
Okay, thank you, Mariana. Hello, everybody. My name is Jorge Lorenzo, and I am head of Water and Packaging Department in CNTA. CNTA is a center of technology and research that support to the food industry. I'm co-worker Eva Petri, last speaker. I also have been the responsible of activity PHB, compostability, and biodegradability in the BioBarr project. Briefly, I would like to explain you how has been the CNTA work plan for evaluating from a biodegradability and compostability point of view the polymers based on PHBs which have been developed in BioBarr project. First, we will talk about the objectives of this task, which will then be set out by the activities carried out. Secondly, we will talk about the applied methods and their modification to be able to be carried out. And finally, we will talk about the result obtained and the general conclusions. So our objective was to verify the biodegradability and compostability of the different prototypes, which at the end they have been 11 prototypes of polymers based on PHB developed throughout the BioBarr project. Talking about standard reference, this scheme sums at the stage which UNA standard required for carry out the biodegradability and compostability test. As you can see, those tests are divided in 4 essays. First, chemical characterization, which include quantification of the volatile solids and heavy metals. Secondly, biodegradability test. Thirdly, essay about material disintegration. And finally, the ecotoxicity test. In both, you can see criteria which are established for considering okay or not okay the assay results. Methods and criteria. Regarding the first essay, chemical characterization, assays pretend to study the toxicity of the tested materials. There are 2 methods. Volatile solids, where polymer sample is introduced in an oven at 550 degrees during 16 hours, and after incineration, what is weighted and its salt be lower than the 50% of the total initial sample amount. And the other method, heavy metals, films materials, prototypes were previously digested and analyzed by ICP. For example, heavy metals, for example, arsenic, lead, cadmium, chromium, copper, molybdenum, nickel, mercury, selenium, zinc, and fluorine were quantified. Secondly, biodegradability is focused in quantify how long is necessary for getting the material consumption by microorganisms. Cellulose, a recognized biodegradable material, is used as reference, and essays compare the oxygen demand, BOD, of microorganisms which are using the tested material with the cellulose, and with this the theoretical consumption based on its chemical formula. Regarding compostability, according with the UNE standard, 3 months would be enough for getting total disintegration of the samples. However, after these 3 months, we observe some big fragments of the polymer material without disintegration, especially in the metallized sample. And we decide to extend the test 3 months more, because what we wanted to observe is the disintegration capacity of the samples. Regarding the last essay, after selecting those prototypes which had fulfilled with the previously tested criteria, we carry out the ecotoxicity test. For carrying out it, we used the plant specia Edaria helix, and we measured its growth capacitability on 2 kinds of compost: commercial compost, a reference growth criteria, and on our compost produced for the previously disintegration test. After 2 months, vegetal growth was measured and commercial compost was compared with the polymeric composting in order to quantify difference. The slide shows some examples of the BioBarr samples which have been tested in the assays. First image shows some example of film base of PHBBs. In the middle, you can see two examples of bioinks printed by Chemigraph partner, and on the right, you can see one image of the 3 final prototypes which were developed based on PHB with a different treatment carried by its Mendue partner. Alox treatment, metallize, and multi-layer PHB, PLA. Talking about results, this first table shows all the results obtained from the first essay, material characterization. Here we see the results of volatile solid, and here we see the results of heavy metals in the different prototypes. As you can see, all the polymeric prototypes, PHBB, PHB, multilayer, pass the legal requirement of volatile solid and heavy metal content. Up in the table, you can see the plus criteria. Regarding the second essay, biodegradability, as you can see in this table, our first prototypes passed the criteria of biodegradability. The criteria is 90%. Similar result with bioinks. The two test bioinks, because one is the control, fulfills with the biodegradability criteria too. And finally, this table shows result of biodegradability assay with the 4 final prototypes. As you can see, these polymers also pass the biodegradability requirement. Therefore, we tested the compostability assay with these 3 prototypes, and this integration test showed that the 3 ones were able to be compostable in 6 months approximately. The important thing we want to observe in this activity is whether the samples had the ability to disintegrate. And finally, these 3 last prototypes passed the ecotoxicity test. The 3 final prototypes passed the criteria. As conclusions, all test prototypes can be considered safe from a chemical point of view. All tested prototypes have been biodegradable. And finally, last 3 prototypes based on PHB with a different treatments, Alox, metallize, and multilayer PHB PLA, will be the polymeric prototypes which will fulfill with all the technical criteria for being considered biodegradable and have the capacity to be compostable. But it's recommended repeat the disintegration test strictly following the reference standard to ensure the result obtained, because the modification made, time and sample amount, could not obtain a certificate of compostability. And this is all. Thank you very much for your attention.
Thank you, Jorge. Okay, we are perfectly in line, so we can continue with the DTU which will start with life cycle analysis, and then we'll continue briefly with cost-benefit analysis. So, Nikolai, the floor is yours.
Thank you very much, Marianna. Yeah, thank you all for being here today. I will present first results of life cycle assessment, followed by cost-benefit analysis. Let me just share my screen. Yes, can you see it?
Yes.
Okay, perfect. Yes, my name is Mikołaj Owsianiak. I'm from Technical University of Denmark. And we've been involved in the project looking into environmental performance of the PHA-based polymers, and I'm happy to present some of the results that we got. So very briefly, what we compared is, or the goal of the LCA was to identify environmental weak points of the PHA-based polymers to improve barrier properties. So weak points, we also refer to them as hotspots, environmental hotspots. So we looked at PHA functionalized by metallization with aluminium, also treated with aluminium oxide, or combined with PLA, so bio-based PLA. So we also compared these packaging materials with existing alternatives like fossil-based PE or PP, like you can see here, but also the PLA itself. And we did it for the functional unit, which represents a packaging of 1 croissant. So here you can see actual example of how croissant is packed with or wrapped with PHA combined with PLA. So technical details of the LCA, functional unit, carefully defined, protection of 1 average croissant, taken as an exemplar of a dry product against migration of oxygen, water, and aromas during transport and storage for 30 days with some technical requirements that have to be met. So LCA is about systems, so we have a systems perspective. We consider the full life cycle from cradle to grave. So we looked at the feedstock, all the pre-treatment, fermentation, recovery, and purification steps, functionalization, printing, and to the final disposal. We also look at incumbent use of the feedstock. In this case, we modeled feedstock was molasses, so we had to look into what is the current use of molasses and consider that in the LCA as well. Life cycle inventory modeling was done according to ISO and European guidelines as presented in ILCD. We choose to work with attributional modeling framework, which implies that it's very technical detail, but it's quite important for the results, which is why I mentioned that now. It implies that system expansion is the preferred way of handling multifunctional processes, and background system is to be modeled using average processes. This has some implication on the results. Now, the data for the PHA installations, the whole fermentation and post-treatment, we modeled that based on data, mainly measured data retrieved from literature review. So we found 25 papers which present technical details of PHA production. And from these 25 papers, we identified 4 which have the data that we actually need. So we needed data on a pilot scale and full-scale production, ideally from molasses, using Ralstonia as fermenting microbe. So we collected data on yields, bill of materials, energy use, and so on. So this is for the PHA installation. For the functionalization, well, we had project partners who were able to provide some data on that, so we used measured data from the project partners. Briefly about how impact assessment was done, we used recipe 2016 as starting point. So we used 17 midpoint impact categories from recipe. So acidification, eutrophication, land use, water use, that's from recipe. For greenhouse gas accounting, we use global warming potential 100, common indicator, with credits for temporary carbon storage. That's relevant for biodegradable bioplastics, as there is some benefit from carbon storage that we wanted to capture. We additionally use the global temperature change potential. It's a metric that has recently been recommended by LCA community to use. It's also recommended by IPCC. And the novelty here is that we actually added we modeled new indicator, new metric called multiple climate tipping points potential. I'm not going to go through all technical details of what the indicator represents, but essentially it allows us to capture the impact to crossing climate tipping points. This is quite novel. This is a new method. It's not meant to replace what we have today, like GWP or GTP. It complements the existing metrics. So we have also results for this new set of indicators. Now, jumping to the results, this is the snapshot of contributing processes for PHA production in Italy at large scale from molasses. So you can see that the dark blue colors, this is actually the use of molasses as feedstock, and it can be explained by the fact that when you use molasses as feedstock for PHA production, you don't use it for something else, and that something else is production of animal feed. So that animal feed has to be produced from alternative sources like barley grains, for example, and this is what you see here. So there is quite high contribution from the feedstock in this particular setup. We can also see a little bit from the recovery and purification step, a little bit from the fermentation. So these are the weak points. I think it can be concluded that the feedstock, this feedstock is the weak point. Now, the previous presentation showed or confirmed that PHA plastics, even if treated, functionalized, is biodegradable, but we don't necessarily know how biodegradable it is in the environment, in the landfilling conditions, for example. And this may have some implication on climate performance. So we compare different scenarios where we assume different biodegradation kinetics, from very fast, 90% degradation in 2 years, to very small, 1% degradation, 100 years, and some intermediate ones. And we see that the impacts are higher. So the red colors represent higher impact. They are higher for faster degrading polymers. This is due to the fact that benefits from temporary carbon storage are not considered if polymer degrades fast. For comparison with the new indicator, the climate tipping point potentials, we see that biodegradable polymers actually perform better than those which have higher stability. And there is a reason for that. The reason is that for these intermediately stable polymers, most of greenhouse gases from landfilling will be emitted close to the point where, in time when probability to cross tipping points, projected tipping points, is the largest. So there is some added value from using alternative metrics. Now, perhaps the most interesting set of results, comparison with alternative polymers. So what you can see here is impact for PHA, different thicknesses, different ways of functionalization as they depend on the yield of PHA from the feedstock. So the higher the yield, the lower the impact. This is for the use of fossil resources. And we wanted to see how it compares with fossil-based like PE or PP, but also the PLA. So what we can conclude from this picture is that, from this figure, is that if the yield is improved, PHA of thickness comparable to the thickness of currently used polymers can compete with PLA. Not quite there yet in terms of comparison with PE or PP, but it's not very far. So to conclude this presentation, the main findings are that LCA showed that sugar beet molasses is an environmental weak point. And I think we have a reason to believe that considering second generation feedstocks will improve performance. It depends. PHA yield is quite important for the environmental impact, environmental performance. So it's very natural to focus on achieving high yield when scaling up or implementing the technology. Further product optimization may be necessary for PHA to perform better than existing alternatives. So reduction of thickness, if technologically possible, of course, is the way to go, combined perhaps with different feedstock. And determining the most climate-friendly PHA-based polymer is not so straightforward, and that's because we know little about mineralization biodegradation kinetics in the environment. That's one thing, but also because different metrics, different indicators can lead to different conclusions. So we need to be able to weigh them. This is it for the LCA part. I'd be happy to answer questions if there are any. And I think I will jump to the cost-benefit analysis immediately. By the way, there is a further reading of this. We published those results in papers. Details about the new metric and how it was implemented in the LCA can be readily found in open access papers. So if you're interested, feel free to look this up further. Now, cost-benefit analysis. It was done for the same system, for the same unit, so packaging of 1 croissant. And we wanted to identify economic weak points in this case, so not environmental but economic. And we wanted to estimate the magnitude of the revenues that is needed to make the PHA-based polymers a sound investment in the packaging sector. So we calculated the present value of cost and the present value of benefits. And we would like to be in the situation where the present value of benefits is higher than the present value of cost. So this is not the true result. This is where we want to be. Now, for the present value of cost, we consider the following cost: the cost of feedstock, the molasses in this case, capital and operational expenditures from the PHA production and filmmaking and functionalization. So for the PHA production, we base the cost on literature values. For functionalization and printing, we got data from project partners. We have a cost of substitution, which is the cost of production of animal feed from barley that needs to be considered when we use molasses as feedstock. We have a cost of bio-waste treatment, so end of life of packaging, and externalities. So these are environmental impacts which are expressed in monetary terms. For the default set of values, default set of costs, this is how the present value of cost look like. We can see it's about 7 euro cents per packaging of 1 croissant, roughly speaking. The largest contributor to the present value of cost is the cost of externalities, so monetized environmental impacts from the LCA. The cost of PHA production, functionalization, and so on, all together represent another 1/3 of total present value of cost, the green bars here. Now, there is large uncertainty about these values because the costs, well, they can differ quite a bit depending on how PHA is produced and so on. So we altogether defined 18 scenarios which represent variability and uncertainty in the underlying data. These are the results for all the 18 scenarios in addition to the baseline scenario. So for example, in scenario 1, we took the costs which are in lowest range of possible values. In scenario 2, we took the values which are in higher range of the costs which are in higher range of values, and we have a different combination as intermediate. So you can see that some scenarios result in pretty high present value of cost, And this is because of different methods used to monetize environmental impacts. There is large uncertainty about different methods, different approaches, and this is what you see here. Now, for the present value of benefits, we identified the two main contributors to the present value of benefits that should be considered. The first one is benefit from the revenues of sale of PHA-based polymers as packaging. The second one is benefit from barrier properties. So this could, for example, be the benefit which is due to increasing sale of croissant because it has bio-based biodegradable packaging, for example. Now, this benefit was very challenging to estimate. We didn't have any data on this, and we didn't want to speculate too much. So we set this benefits from cost or benefits from barrier properties as equal to 0. We also didn't have much on the cost of revenues, but what we could do, we could calculate the range of revenues that would make the PHA-based polymers a sound investment when you compare them with the present value of cost. And here is the result. So the present value of benefits is equal to the benefits from revenue of packaging sale. So as revenues increase, the present value of benefits increase because C barriers is equal to 0. Now we can compare that with the present value of cost. Of course, it's independent on the benefits from the revenue, but it's uncertain, as I showed. So this is variability across all 18 scenarios, from 4.5 cents to 33 euro cents. Now, comparing these two numbers, we can see that the revenue should be in range of 4.5 to 33 euro cents in order for benefits to be equal to cost. So if you compute net present value as the difference between present value of benefits and present value of cost, it's pretty obvious at how high the revenues should be in order for the net present value to be above 0. So in using this type of analysis, we showed that the benefits from revenues of PHA-based plastic packaging should be in that range or higher per 1 croissant to compensate the present value of cost. We don't know if it's realistic to achieve, but this is the number we get basing on the best data we could identify. We also found that monetized environmental impacts are the largest contributors to the present value of cost. So just from purely economic perspective, of course, these benefits will be reduced if you don't consider cost on the environment. And we also found that sugar beet molasses used as feedstock is an economic weak point, so it's natural to do similar analysis for other feedstocks at some point. Thank you very much for listening. I'd be happy to take questions.
Thank you so much, Mikolai. I think we can have a look at the chat. In the meantime, I think we can go on. I will close this workshop in terms of presentations, starting with the value chain analysis and then with the final conclusions. So. Okay, so inside this project, it was expected also to carry out, in addition to the life cycle assessment and to the cost-benefit analysis, also a value chain analysis. So the main objective, understanding how each company along the supply chain creates value and looking for ways to add more value are critical elements in developing a competitive strategy for the new supply chain here proposed. So the value chain analysis represents a means of evaluating each of the activities in a company's value chain to understand where opportunities for improvement lie. Conducting a value chain analysis prompts to consider how each step adds or subtracts value from the product, which in our case is represented respectively from feedstock to packaging solution, passing through the PHA granules, the PHA-based flexible films, and the functionalized flexible films. These, in turn, can help the supply chain players to realize some form of competitive advantage, such as, for example, a cost reduction by making each activity in the value chain more efficient and therefore less expensive once identified where the main problems are. And investing maybe more time and resources into activities like research and development, design, or marketing that can help the product stand out. So this is mainly a tool useful for the players for understanding where is possible to act for improvements and cost reductions. We have applied a method which is the innovative FAO method. And in terms of value chain analysis methodology, we have foreseen 3 main steps. So the first one, mapping the BioBarr value chain. So 4 sub-steps, setting the boundaries. So the analysis need to be limited in its actions and interests, identifying the activities carried out along the value chain, identifying the agents, so the players, the actors, and quantifying the physical flows. Then we have determined the cost and value of activities in terms of net value added, which was calculated. And in theory, the price must, on average, cover costs of inputs purchased from third parties, wages and salaries of employees, and provide an adequate return to company. Once compiled the value chain and understood the cost and value associated with each step, we analyzed it through the lens of whatever competitive advantage the supply chain is trying to achieve. So this is a flow chart which puts in evidence the value chain steps which we have taken into consideration. So we have put ourselves in the condition that this should be a value chain, an ideal value chain soon after the BioBarr project with industrial players, so where a scale-up has been done. We have excluded the packaging use and disposal, which was not considered into the project, and we have not taken into consideration in this analysis. So this was, for example, one of the boundaries. So the main findings, the PHA producer is the actor who generates the higher value in the BioBarr value chain. Despite investments in equipment, processes, optimization, on its side, it has the exclusivity. Indeed, being there few producers of PHA on the market in this moment, it can still dictate the price. Obviously, the price is related to the production quantity, measured demand for production, for example, in terms of tons, and the lowest price per kilogram. The food industry discloses an NVA, which is the second largest value, originated by a high value of the output and the possibility to maintain a higher price on the shelf, the green characteristics of packaging. And through this value chain analysis, we understood once more, as already put in evidence, for example, in the LCA and in the CBA, how much feedstock choice influences the generation of value and not only impacts on environmental aspects, which steps could be more efficient. For example, energy consumption results to be one of the main cost drivers for all agents, and how much important is, for example, to shift towards green solutions or to optimize the process, and how much important are future investments in research and innovation. Then, obviously, this was just a value chain analysis, a preliminary value chain analysis, and it was done according to our assumptions and our considerations. And so there is the need to carry out in the future comparative studies, changing, for example, some parameters as the feedstock. So what happens in this analysis is if we do not use molasses, but something different, and optimizing processes which, as said, are not completely optimized in this moment. And now I would like to end all the presentations with some final conclusions. So we have spent together 2 hours and a half hearing about the different projects beneficiaries. And here I would like to put everything together. So first of all, I want to put in evidence as BioBarr was a very finalized project with the limited boundaries. I mean, it is not possible in a research and innovation project to put everything inside, as you can imagine. So we made some choices at the very beginning, drafting this proposal, and we decided that the main focus had to be on the PHA production feasibility, investigation of PHA-based, so PHB, PHBV granules processability in flexible films for food packaging applications, and investigation of PHA-based films functionalization. It was a RIA, so a research and innovation action. It was a proof of concept with a TRL 5. What was out? It was not included into our investigations an in-depth study on different feedstocks. It was not our main focus. As said, our main focus was on technologies. So we wanted to understand what about extrusion, what about functionalization, and how these processes influence in some way the material behavior and applicability. So we have not focused on feedstocks because we know that PHA can be produced from different feedstocks. We are aware about this, but it was not possible to process everything and to compare the different situations, because as you can imagine, it requires time, but it requires also the revision, for example, at the upstream phase of the process, because each feedstock needs different fermentation conditions and so on. So we decided, according to our different reasons, to focus on one of them, which was molasses. We understood that it was probably not the best solution, but it was made also according to a proximity reason. I mean that at the very beginning of the project, the food producer of sugar was very close to the facility of the PHA producer, and so also for saving costs in transportation and also with an eye to the environmental impact, we decided that proximity was a good solution, and but also for different other types of reasons. Another point which was out is the injection molding. So I mean that rigid and semi-rigid trays were out of scope in our project. We focused only on flexible food packaging solutions, so in films. We have not tested PHA behavior in these different types, even if we know that a lot of projects are carrying out also these type of activities. Another point which was out from our investigations was the study of end of life and the related waste management. So, for example, the recyclability. So we have not focused on what will happen to BioBarr project once on the market. It was not included in this study. We decided to stop to the validation at the end user. even if I want to put in evidence that some analysis and some considerations have been included in CBA and LCA. And then we have not investigated the storage conditions. I mean, we have not analyzed what happens to this new material, to the reels, one stored in the warehouse, how many times can be remain there, and so on. In general terms, we can say that samples are still there, also after a lot of time. So probably this material is resistant, even if we know that is a little bit more fragile and delicate compared to the current fossil-based materials used. In BioBarr, there were a lot of challenges faced. So we had to work in these 54 months on the study of the right formulation for improving the yield, which is very important for making all the supply chain working properly and be in some way good enough also for providing some benefits in terms of costs. We had to optimize the processes of fermentation, of recovery, purification, and compounding. And this has been done thanks to the following activities. So each time after a trial, there was a feedback to come back and to optimize everything. So revising the aspects which was weak for improving them. So a lot of loops and trials. Another challenge was understanding more on PHA granules, so the mechanical, the barrier properties, the right choice of additives, because these are very important for providing the right functionalities to the field, but at the same time they can migrate, they can in some way impact on the runnability of the material. So these are this choice is very important. And we understood also how this step impacts along the supply chain. We had to study the extrusion phase, so the right screw, the right speed, the right parameters, the film thickness for avoiding pinholes. We had to test the processability through existing equipments, because at the very beginning we were not completely aware that for all of the steps of the supply chain it was possible to use equipments usually into the facilities. And we had to study new co-extrusion, lamination and surface treatments, including corona treatment, as well as the adhesion and the printing conditions, sealing and packing. So our general recommendations according to the evidences coming from BioBarr project is to pay attention to choose a feedstock which represents, as already said by Nicolai in his presentation, a real waste. So a second generation feedstock, as has said, which has to be in some way disposed, which has no alternatives, because this can strongly impact on LCA, CBA, and value chain analysis. To pay attention, as already said, to the additives choice, because they can involve fragility, better runnability, migration on the surface, problems in multi-layers adhesion, and or on printability. In terms of lessons learned and evidences, we can say that the use of waste from agri-food sector as feedstock can influence the costs and the added value along the supply chain. Obviously, the possibility to start from a waste means to have some costs saved along the supply chain. How much important is a strict collaboration among players, because it is possible to optimize the final product, collaborating all together and optimizing the process. PHB and PHBV in particular can be produced, intervening also in cost reduction For example, optimization of energy consumption in the last step of the recovery phase, that is the drying phase. A reduction of chemical consumption in production process is feasible. And we have understood that PHB, PHBV can be processed through the typical technologies of thermoplastics. I have put here a note. Obviously, what I'm saying now is according to our studies and conditions, because limitations in some studies need to be taken into consideration when some BioBarr projects results are assessed in future follow-up actions. Then we have understood that co-extrusion or blending are the best technological solutions for PHB. Obviously, there is still the need to investigate more on the best copolymer. Co-extruded films can be then oriented, laminated, or processed in other ways, as is done for single-layer materials. Lamination is feasible, need to investigate more on the best copolymer for multi-layers, also in this case. The material is suitable for printing, both with traditional inks and with compostable bio-based ones. It is suitable for food contact, even if I know that there are some doubts in relation that what happens if these new materials comes from a waste. And we have demonstrated that it is compostable and biodegradable, even if we cannot certify it. LCA is a relevant tool at support of research and innovation projects and guide product optimization. Current LCA on the relative immature PHA technology showed where to focus to make PHA-based polymers perform better than existing alternatives, but limitations and data gaps need to be considered, as well as that the process is not optimized yet and that there are a lot of margins of improvements for changing the final result. PHA-based films treated with aluminum or aluminum oxide are fine for packing, for example, fresh fruits, vegetables, and potentially also for bakery dairy products, according to the barrier properties measured. New compostable and bio-based inks are reaching the market. However, there is still something which remains to do. There is the need to increase PHA production capacity and the related PHA yield also when scaled up. In fact, Nikolai put in evidence as in the scale up, it seems that there is a low PHA yield compared to the pilot line. Test also other feedstocks, both under the technical as well as LCA, CDA, and value chain point of view. Reduce as much as possible the PHA thickness, possibly, for example, to 30 micron, because currently we have used films which were more or less from 50 to 70, 80 micron. And the challenge is to reduce this thickness, avoiding the presence of phenols and maintaining good mechanical and barrier properties. Some more investigations are needed, so to move these results towards a TRL of 7, 8, example giving in the improvement of the material's fragility, extrusion trials and following steps should be conducted all at industrial scale. Co-extrusion or blending solutions have to be investigated more. In terms of biodegradability, even if our results are very good and promising, we suggest to repeat tests using standard for obtaining certification. And obviously, we understood that potentially the new bio-based ink developed into the project by Cow Chemigraph is compostable, but it has to be still certified OK compost. So, in general terms, I start thanking all of you for participating, attending this workshop, because for us it was important in some way to share the knowledge outside, both with the scientific community and with the industrial representatives. Scientific community because can start from these results, compare with the results they have and to go on, and for the industry for understanding how far this material is for a concrete application in real conditions on the market. So if I have to answer, is this product already marketable? I have to say not yet, but we are in the right direction for obtaining this. So okay, then here I see that some comments are included, and in theory we will try to answer to your doubts. So we have taken note and we will try to answer to your doubts. Thank you, Jan, for your comments, which I followed along the presentations. Very interesting, and we will go in deep into all of them. And for sure, we will have a look also to the projects you mentioned into the chat for understanding more. And let's take into consideration for the scientific community who follow this workshop, in the case to collaborate also for future actions and for next advancement in the field. So Raffaello, are you there?
Yes, okay. Yes, I'm here. Yes, Marianna, I'm here.
Yeah, okay. If you agree, I think we can take note of all the comments and questions, and we can answer to these people also after the event, if you agree.
Absolutely, yes. Thank you to everybody. It was very interesting. Thank you for the
yeah. We will let you know about the presentations, in which way we can share them with you. And probably being this event recorded, we will try to put these online so that it can be looked also by other people. So I think we can close this presentation. Anna, thank you for attending. And so I think we can close the session. Thank you so much.